What specific problem does the new method or algorithm aim to solve?
The new method or algorithm aims to solve the specific problem of implicit reasoning deficiencies in large language models, LLMs, particularly in the context of inducing structured and compressed representations of facts and rules during training. The method focuses on addressing the limitations of LLMs in performing implicit reasoning tasks, such as composing internalized facts and comparing entities' attributes, by studying the acquisition of implicit reasoning skills through grokking. The goal is to understand how transformers can learn to perform implicit reasoning by inducing and applying latent rules over knowledge in a generalizable way. The method aims to investigate the fundamental limitations of transformers that hinder the robust acquisition of implicit reasoning skills, and to explore the factors that influence the model's generalization capabilities, especially in distribution, ID, and out-of-distribution, OOD scenarios. Ultimately, the algorithm aims to deepen the understanding of the grokking phenomenon and to provide insights into improving transformers' generalization abilities for complex reasoning tasks.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method works by training transformers to perform implicit reasoning through a process called grokking. This involves constructing synthetic training and evaluation datasets, training transformers from scratch, and evaluating their generalization. Reasoning is conceptualized as the induction and application of inference rules, where the model is exposed to a mixture of atomic facts and inferred facts, resembling axioms and theorems in a formal system. The model's ability to make novel deductions is tested in both in-distribution ID and out-of-distribution OOD scenarios. The experiments reveal that transformers can learn implicit reasoning, but this skill is robustly acquired through extended training far beyond overfitting. The speed of improvement in generalization correlates with the ratio between inferred and atomic facts in training, rather than the absolute size of the training data. The model exhibits different levels of systematicity across reasoning types, with consistent ID generalization, but varying OOD generalization performance. Mechanistic analysis of the model's internal mechanisms uncovers the gradual formation of a generalizing circuit throughout grokking, establishing the connection between systematicity and its configuration. Proper cross-layer memory, sharing mechanisms for transformers such as memory augmentation and explicit recurrence, are needed to further unlock the model's generalization capabilities. The method showcases the power and potential of parametric memory for complex reasoning tasks, demonstrating that a fully grokked transformer can achieve near-perfect accuracy on challenging reasoning tasks with large search spaces, outperforming state-of-the-art models based on non-parametric memory.
What are the theoretical or practical benefits of using this method?
The theoretical and practical benefits of using the method described in the paper include the ability to enhance transformer models' reasoning capabilities through grokking, which allows for the acquisition of implicit reasoning skills over knowledge. This method enables transformers to learn to perform complex reasoning tasks by inducing and applying latent rules in a generalizable manner. Through controlled experiments, the method reveals that transformers can acquire systematic generalization through extended training, far beyond overfitting, leading to improved performance on both in-distribution and out-of-distribution scenarios. The method also provides insights into the inner workings of the model during grokking, uncovering the formation of a generalizing circuit that facilitates deep compression and integration of information for complex reasoning tasks. Additionally, the method highlights the importance of parametric memory for deep compression and integration of information, showcasing the unique capability of transformers to achieve near-perfect accuracy on difficult reasoning tasks with large search spaces, which are out of reach for models based on non-parametric memory. Overall, the method offers a systematic approach to understanding and improving transformers' reasoning abilities, paving the way for advancements in natural language processing tasks requiring complex reasoning and generalization.
How is the method validated or tested?
The method is validated or tested by constructing synthetic training and evaluation datasets, training transformers from scratch, and examining their generalization. The researchers conceptualize reasoning as the induction and application of inference rules, exposing the model to a mixture of atomic facts and inferred facts resembling axioms and theorems in a formal system. The model's ability to make novel deductions is tested in both in-distribution (ID) and out-of-distribution (OOD) scenarios. The experiments reveal that transformers can learn implicit reasoning, but this skill is only robustly acquired through extended training far beyond overfitting, a phenomenon known as grokking. The speed of improvement in generalization correlates with the ratio between inferred and atomic facts in training, and depends little on the absolute size of the training data. The approach allows for controlled training data and clean evaluations, providing insights into the transformer's generalization capabilities. The results of the experiments showcase the transformer's ability to acquire compositionality and systematic generalization through grokking, shedding light on the importance of data distribution in characterizing the model's generalization. The researchers also conduct mechanistic analysis of the internal mechanisms of the model to understand why grokking happens and why transformers struggle with OOD examples.
What results were achieved with this new method?
The new method achieved significant results in the study of transformers' implicit reasoning capabilities. The experiments revealed that transformers can learn implicit reasoning through a phenomenon called grokking, where the model acquires the skill of implicit reasoning through extended training beyond overfitting. The study showed that the speed of generalization is influenced by the ratio between inferred and atomic facts in training data, rather than the absolute size of the data. The findings demonstrated that transformers can acquire the rule of composition through grokking, with controlled experiments highlighting the crucial role of data distribution, specifically the inferred atomic ratio, in characterizing the model's generalization. Additionally, the study showcased the transformer's ability to learn systematic generalization for comparison tasks through grokking, where a parallel circuit is learned by the transformer. Furthermore, the research illustrated the power of parametric memory for complex reasoning tasks, showing that a fully grokked transformer can achieve near-perfect accuracy on difficult reasoning tasks with a large search space, outperforming state-of-the-art models based on non-parametric memory.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method presented in the paper include the failure of models based on non-parametric memory, such as GPT-4 Turbo and Gemini PRO-1. 5. To perform well on a difficult reasoning task with a large search space. These models struggle to reason deeply and achieve near-perfect accuracy, unlike the grokked transformer which excels in solving the task. Additionally, when prompted to reason verbally, the non-parametric memory-based models tend to give up and make incorrect rationales, showcasing their inability to reason effectively. Furthermore, the non-parametric memory-based models perform worse when prompted to reason verbally compared to direct answer prediction. This highlights the current model's limitations in reasoning deeply with non-parametric memory. The paper also suggests that while the grokked transformer can achieve near-perfect accuracy on complex reasoning tasks, there is a need for further research to understand the trade-off between parametric and non-parametric memory in language models to enhance their generalization capabilities.
What future work do the authors suggest?
The authors suggest that future work should focus on understanding the trade-off between parametric and non-parametric memory in language models. They highlight the complementary nature of these two types of memory, where parametric memory excels in compressing and integrating information but may lead to hallucinations, while non-parametric memory is lossless and can provide attribution. The authors propose exploring how to define the objective for balancing these two types of memory effectively. Additionally, they suggest investigating the role of verbalizations in reasoning problems and developing methods to determine the appropriate balance between implicit and explicit reasoning for handling complex problems with large intrinsic complexity. Furthermore, the authors recommend further research on the role of verbalizations in reasoning tasks and understanding the impact of verbalizing intermediate knowledge and reasoning steps during inference. They also propose exploring the potential benefits of verbalizations in improving performance, especially for large models with strong generation capabilities.